Let's have a look at some results. If we've got a polynomial and we know it's got k distinct zeros, then we know that each one of those will produce a linear factor. Therefore, whatever x minus a1 times x minus a2 and so on expands out to be, that's got to be a factor of the polynomial. And we get something like this. So we're going to show that both 1 and -2 are zeros of this polynomial, and then we'll go and factorise the whole thing. We subbed into our polynomial. Yes, polynomial 1 is 0. Polynomial -2 is 0 as well. Therefore we know that x minus 1, x plus 2 must be a factor. Well, I'll expand it out to make the other factor easier to work out. So leading term times leading term, we must have x squared. Constant times constant, we must have 5. What is the missing term? At this stage, if I expand out, I would have 5x. Does that mean we've done it? It does. So there it is. X minus 1, x plus 2, x squared plus 5 is our factorisation. So take that a step further. If we know it's of degree n, and then we've got n distinct zeros, then we must have the complete factorisation, because you can't have more zeros than the degree. Alright, so a polynomial of degree n cannot have more than n. Now, we know a polynomial has a double zero at -7. So that zero appears twice. And a single zero at 2. Write down a possible polynomial. By a possible polynomial, I guess they're saying, give me a generalisation that would cover every possible polynomial. I know x minus 2 is a factor, but I also know x plus 7 squared must be a factor, because it's a double zero. It appears twice. It could also be multiplied by some other polynomial though, because they haven't told me anything about the overall degree of the polynomial. However, what I do know about this other polynomial that it multiplies with is that polynomial can't have a 0 at 2 or -7. Otherwise, that would change the nature of those zeros. For instance, if you had another one at -7, it no longer would be a double zero. It might become a triple zero. So it can't be. This one here, do I need it or don't I need it? I guess what I'm saying is I could have any multiple of that. It would still be, but do I really need it? Because that multiple could be in QX itself. So whether I put it down or I don't, it probably doesn't matter, but K would be some real number. If they narrow it down a bit and say, well, what if it's a monic polynomial of degree 3? Well, if it's monic, then that's the only possibility, because that would expand out to give me x cubed. They've told me it's of degree 3, so I know there's no other factor at all. What if it was monic of degree 4? Okay, well again, x minus 2, x plus 7 squared would certainly produce a monic, but as we just saw, that would be of degree 3. To make it of degree 4, it would have to be multiplied by some other linear factor, but again, 2 or -7 could not be a 0 of that linear factor. So a could not be 2 and it could not be -7. Polynomial of degree 5. Okay, again, we know we've got those two basic factors. I'm going to multiply by QX. It's a polynomial of degree 2, and it does not have a 0 at 2 or -7. Again, whether I need that K or not, see, it's not monic, but that K could be in the QX. Alright, here's my contradiction though. Because we just said, if it's of degree n, it can't have more than n zeros. So therefore, if it's of degree n and it does have more than n zeros, but hang on, you just said that couldn't happen. Well, there is one situation where it could happen, and that's if that polynomial is the zero polynomial. See, the number 0 is a polynomial. It satisfies the requirements. But how many zeros does it have? Well, it has an infinite number, because it doesn't matter what you substitute in, you'll get the answer 0. So if you have a situation where you've got a polynomial of degree n, and you know it's got more than n zeros, the only thing it could possibly be is the 0 polynomial. Notice I've used the congruence symbol there rather than the equals one, because congruence means identically equal in every respect. In fact, they are the same thing. If you were to draw them on, they would sit on top of each other. But they are identically equal. Well, if that's true, then the coefficients of each one must be equal, because we're basically saying they're the same polynomial. So I have to solve something like this, then I know, well, I'll just solve the coefficients. So A1 must equal A2, B1 must equal B2, and so on for every term, because they are identical rather than equal. Right? See, if it's equal, they might just be equal in one or two places. But when we're saying they're identical, they're always true no matter the value of x. Okay, so 10e will play around with some of these results.